we define the length of a plane curve with parametric equation. Then we have x equal f of t, y equal g of t. We have this from a to b. I forget about that. Then we have the length is equal to integral from a to b. The first derivative of the first equation is f of t plus we have the first derivative of g of t square dt. Using the same concept, we have right here two space curve. We have x equal f of t, y equal g of t from n, z equal h of t from a to b. This from a to b. Now we have something going on. The integral from a to b of f of t, first derivative of that square plus the derivative of g of t square plus the derivative of h of t square dt. Let's do one example to prove this, to show this. We have x t equal 5t. We have yt equal 4t squared, and then we have zt equal 3t squared from 0 to t. Right. So we take the first derivative of everything. We have 5. We have 8t, and then we have 9t. The length of that from t to 0 is going to be 5 squared plus 8t squared plus 9t squared dt. Now we simplify it a little bit. We have 25 plus we have here is 64t squared plus 81t squared. We have 145t square dt, and then we evaluate the integral, and then we will have the answer. Let's move on to vector continuity. Vector continuity. The vector function rt is said to be continuous at t equal t0 for any epsilon greater than 0. Then therefore we have for any delta greater than 0, we have such that the absolute value of rt minus absolute minus rt is less than epsilon. Equivalent to, we have t minus t naught is less than the delta. You know, if r is rt is defined as position function ft, gt, and h of t, then the velocity and acceleration vector is going to be the first derivative of rt and the acceleration vector is the second derivative of rt in classical physics. To know the equation of motion of a particle, we have two things. The first thing is position. And velocity. These are the first two things we need to know. And RT is defined as the position of the particle at any time, at any given time. Any given time. Then with a very small change in time, let's call the change in time, we call that change in time. We call that delta t. And certainly we have this plus delta t plus delta t. So the change in position is equal delta RT equal R plus delta T minus the function itself. Then the average speed is equal to R T plus T naught plus delta T minus RT over delta T. Let's look at projectile motion. If acceleration and initial velocity and position are given, we are given acceleration, the initial velocity, and position, then we can find the velocity and position vector by simple integration. To find the velocity, we can indeed find the velocity and the position vector, which is rt, and we represent it as r. Let's turn the axis in the direction so that the particle moves on the xy plane. Now let's look at this. We have angle theta here. As we tell something angle theta, we have y-axis and x-axis. We have f equal and times acceleration itself. And acceleration itself divided by 0 negative g cavity. As the cavity always pointing downward, then therefore we have negative cavity and negative g here. We have the vector of velocity is equal to v cosine of theta negative g times t plus v sine of theta, and the position function is going to be v cosine theta t times t minus g over 2t squared plus v sine theta t plus y naught. Y naught is going to be the initial distance, the initial replacement. Now we look at the unit tangent vector. Unit tangent vector to a curve. The unit tangent vector to a curve is defined as the vector t equal the first derivative of the position vector over the magnitude of the first derivative position vector So to find the tangent line, up to a curve, we have 3 steps. First, we find given the position vector, right? First, we find the first derivative of that, and then we find the unit vector, the magnitude. Second step, at the given time, point, we find time. We find t. And now we use, now the third step, the last one, we use t as we find from the step number 2. We use t to find vector, to find the tangent vector. And then we move on to smooth curve.
So I'm going to talk about the unit normal vector and the binomial vector. The unit normal vector is defined by vector nt will be equal vector t prime t over the magnitude of vector t prime t. We all know that normal vector is orthogonal to the tangent vector because the bottom is the number, so vector t prime is orthogonal to vector t, and I'm gonna prove this one. Let's suppose we have vector rt and the magnitude of vector rt is c for all t. If we dot vector rt with vector rt, it will become the magnitude of vector rt square, and is equal c square. Let's differentiate both sides. Then on the left side we will have vector r prime t dot vector rt plus vector rt dot vector r prime t, and the right side will become 0 since it's a number. So the left side will become 2 r prime t dot rt, and because the dot product of r prime t and rt equals 0, so that means the r prime t is orthogonal to rt. So back from that we will have vector t prime t is orthogonal to vector t t, and because the normal vector n is the unit normal vector, so we'll have vector t prime t over magnitude of vector t prime t. Next, about the binomial vector. The binomial vector is vector bt is defined by vector t t cross vector n t. Because of that, so the binomial vector is orthogonal to vector tangent, and it also is orthogonal to the normal vector. Next, I'm going to talk about a tangent plane, normal plane, and osculating plane. So suppose we have curve here, and then I will use this point. So the tangent vector is going to be this one. A normal vector is going to be this one, and a binormal vector is going to be this. Okay, let me write down. Okay, so the tangent plane is going to be this plane. Okay, the normal plane is gonna be this one. And the osculating plane is gonna be the last one here. The blue. Okay. So how to find a tangent plane? To find a tangent plane, which is the red one, we only need to have a normal vector plus 1 point on this plane. To find the normal plane, we only need to have tangent vector plus point on this plane. And to find osculating plane, we need the binormal vector plus a point. So that's for tangent plane, normal plane, and osculating plane.
Curvature is the measure of how sharply a curve bends, and is defined as the rate of change of the unit tangent vector per unit length, or the absolute value of dt over ds. It can also be written in terms of time as the absolute value of t prime of t over r prime of t, as proven here. An important property of curvature is that a larger curvature has a larger angle difference in their tangent vectors and a smaller radius of curvature. As you can see in this figure, though the pairs of points on this curve P1, Q1 and P2, Q2 have the same distance between each other, the angle produced by their tangent vectors is vastly different. We can also derive an equation for curvature by t using the cross product of r prime and r double prime, which gives us a matrix that produces b vector times ds dt squared. B can be turned into t cross n, and n into t prime. And since the absolute value of t is equal to 1, then the equation becomes r prime cross product r double prime is equal to t absolute value of t prime ds dt squared. And we can rearrange this equation to get the absolute value of t prime is equal to the absolute value of r prime cross r double prime over ds dt squared. And so since kappa equals t prime of t over r prime of t absolute value, we can get the equation r prime cross r double prime absolute value over the absolute value of r prime of t cubed. We can also derive an equation for curvature using rectangular coordinates by first representing a curve C with the equation r of x equals xi plus f of xj plus 0k, where x is the parameter. And the first derivative gives us I plus f prime of xj the absolute value of which then gives us the square root of 1 plus f prime of x squared. R double prime of x is then f double prime of x j. And since R prime of x cross product R prime double prime of x gives us f double prime of x k, we can take the equation kappa equals the absolute value of R prime of x cross product R double prime of x over the absolute value of R prime of x cubed, then plug in the values from our equation and get the absolute value of R double prime of x over 1 plus f prime of x squared all over 2 to the 3 seconds. We can also use curvature in acceleration by starting with the equation for the unit tangent vector and changing it into r prime of t equals the absolute value of r prime of t times the unit tangent vector. From there, we can take the second derivative and get d squared of s over dt times t of t plus ds dt times t of t. And we can change ds dt times t of t into ds dt times dt over ds times ds over dt, which simplifies into v squared times dt over ds. You can change dt over ds to the curvature times the normal vector and get velocity squared over rho times the normal vector, which simplifies into the acceleration of the tangent times the normal vector. Plugging this all back into r prime of t, double prime of t, you can get at times t plus an. From there, you can then make the equation r double prime of t equals dt times the absolute value of v times t plus the absolute value of v times the absolute value of t prime times n equals d squared of s over dt squared times t plus ds dt times the absolute value of v times kappa times n, from which we get the equation r double prime of t equals d squared s dt squared times t plus the curvature times ds dt squared times the normal vector, in which we can see the way that curvature can be applied into acceleration.
Previously, all our vector functions were functions of time. Now, in order to manipulate the unit vectors t, n, and b, we want functions to be functions of arc length. We can achieve this by re-parameterizing curves to be functions of arc length. We use the parametric arc length formula to re-parameterize a curve. S equals integral of the magnitude of r prime dt. First, we take the derivative and then the magnitude. Then we integrate with respect to time. Finally, we solve for arc length and simplify. In this example, we are given the function r, a vector function of time. We take the derivative of r to get r prime, and then take the magnitude of r prime. We then integrate this with respect to time in order to get the arc length. Finally, we simplify to find the vector function as a function of arc length. By doing this, we are able to manipulate curves in terms of arc length instead of time, which leads to some interesting properties. You can take the derivative of any of the unit vectors t and b with respect to arc length. Taking the derivative of the tangent vector with respect to arc length gives you curvature times the normal vector. Taking the derivative of the binormal vector with respect to arc length gives you the negative torsion times the normal vector. Taking the derivative of the normal vector with respect to arc length gives you the negative curvature times the tangent vector plus the torsion times the binormal vector. The content in these chapters are applicable in many different ways. In vectorial mechanics, the net force is the rate of change of momentum with respect to time. For a non-changing mass, the formula simplifies to F equals m dv dt, which is where the famous equation F equals ma comes from. Work is the dot product of force with displacement with a unit of joules. Power is the rate of change of work with respect to time with a unit of watts. Kinetic energy is a scalar. Torque is a force applied on a moment arm and causes objects to rotate. Force applied to the center of the object will produce no rotation. In other words, central force produces no torque. Torque is calculated by taking the cross product of the moment arm and the applied force. Angular momentum is analogous to linear momentum, just as torque is analogous to force. Similarly, the derivative of the angular momentum is a torque. Angular momentum is calculated by taking the cross product of the moment arm and the linear momentum. To graph 3D functions, it is helpful to look at each side of the function. For the function z equals 1 minus y squared, we can look at the xy plane, xz plane, and yz plane. Finally, we put them together to see the 3D graph. Some common 3D surfaces are the quadratic surfaces. These have the form ax squared plus by squared plus cz squared plus dx plus ey plus fc plus g equals 0, with no cross terms. This includes ellipsoids, one-sheet hyperboloids, two-sheet hyperboloids, paraboloids, cones, and hyperbolic paraboloids. Surfaces may also be produced by revolving curves around an axis of symmetry. The surface produced can be found by using the square root of the sum of the squares. For example, for a curve f of xy equals 0 revolved around the x-axis, the surface would be f of x plus or minus the square root of y squared plus z squared equals 0.